Interconnection and signal integrity. A signal change must propagate from the source driver through the bond wire, package LED frame and pin of the source IC along the PCB trace through the pin, LED frame and bond wire of the destination IC and into the receiver. Along this path there are several influences that can cause distortion of the signal and introduce noise. The term signal integrity refers to the degree to which these effects are minimized. The effects include signal skew, ground bounce, transmission line effects, that is overshoot, undershoot and ringing, electromagnetic interference EMI and crosstalk. Signal skew. In common PCB materials, the maximum propagation speed is approximately half the speed of light in vacuum, that is 3 into 10 raised to 8 meter per second divided by 2, which is approximately equal to 150 millimeter per nanosecond. If two traces differ in length, skew at arrival point can be significant. Careful PCB design is needed, hence use CAD tools to tune the PCB traces. Ground bounce. Ground bounce arises when one or more output drivers switch logic levels. During switching, both of the transistors in the driver's output stage are momentarily on and transient current flows from the power supply to ground. There is inductance in both power and the ground connections as shown in figure. The inductance causes voltage spikes in the power supply and ground on the IC. This can cause voltage spikes on other output drivers and shifting of the threshold voltage of receivers on the IC. To reduce the effects of ground bounce, place bypass capacitors between ground and the supply positive. Place a capacitor of value 0.01 microfarad up to 0.1 microfarad close to package pins. Separate PCB planes for ground and positive supply. Limit output slew rate, that is trade-off against power propagation delay. Differential signaling can be used to make the system more immune to noise induced by ground bounce. Transmission line effects. When the transition time between logic levels is similar to or shorter than the propagation delay along a signal path, the transition is affected by reflections at the driving and receiving ends of the path. Reflections interfere with the transitions, resulting in under or overshoot and ringing as shown in figure. This can cause false or multiple switching. Use PCB layout techniques to minimize effects. Electromagnetic interference EMI and crosstalk. Transitions between logic levels on a signal cause electromagnetic fields to propagate around the PCB trace. Some of the field energy is radiated out from the system and may impinge on other electronic systems where it induces noise. This form of unwanted coupling is called electromagnetic interference EMI. There are government and other regulations that limit the amount of EMI that a system may emit in various environments, since excessive EMI can be annoying. For example, if it interferes with your TV reception or a safety hazard. For example, if it interferes with your aircraft navigation. Electromagnetic fields from an aggressor PCB trace can also impinge on adjacent traces, inducing crosstalk on the victim traces. The closer the traces and the longer their parallel paths, the more pronounced the crosstalk effect. EMI and crosstalk can be reduced by appropriate PCB design techniques, limiting slew rates of transitions. Differential signaling. Differential signaling reduces a system's susceptibility to noise. Differential signaling involves transmitting both a positive signal S underscore P and its negation S underscore N and sensing the voltage difference between the two at a receiver. If S underscore P minus S underscore N is a positive voltage, then S is received as the value 1. If S underscore P minus S underscore N is a negative voltage, then S is received as 0. This arrangement is illustrated in figure. The noise is induced equally on the wires of both S underscore P and S underscore N. Such common mode noise is cancelled out when the voltage difference is sensed. Suppose a noise voltage Vn is induced equally on the two wires. At the receiver, the voltage sensed is S underscore P plus Vn whole bracket minus S underscore N plus Vn, which is equal to S underscore P plus Vn minus S underscore N minus Vn, which gives S underscore P minus S underscore N. For the assumption of common mode noise induction to hold, differential signals must be routed along parallel paths on a PCB. The signals are inverses of each other, means that they both change at the same time, so crosstalk effects cancel out. Differential signaling allows common mode noise rejection and improved signal integrity. Improved signal integrity means reduced switching current, reduced ground bounce, reduced EMI, and reduced crosstalk with other signals.